Okay, so this is section 8.3, trigonometric integrals. And you see that in this section, we're going to be studying powers of sine and cosine, as well as powers of secant and tangent. So here you see that those are the two topics, and the first set of guidelines they give us are related to sine and cosine. So you can read through the guidelines and determine if that's what you want to use. I try to teach this where we make sense of it and we're not memorizing a bunch of guidelines. The only guideline that I'm going to refer to is guideline 3, where if we have even powers of sine and cosine, we can convert them using the power reduction formula for sine squared and cos squared. But otherwise, these top two rules, feel free to memorize them if you want to. I'm going to go through problems like this, making sense of the problem as to why we're making the choices for u and du. So if we come down here to example 1, we see that we have a power of sine that is odd and positive. So if we look at this example, we say, what do we want to save for our u substitution? Because I have an even number of cosines, if I take one cosine and save it, I'd be left with sine cubed x and cos cubed x. And if I were saving this for my du, I'd say, well, these are both odd powers. The reason we don't want both of them to be odd powers is I can't convert one to the other using Pythagorean identities unless it is expressed as an even power. So we say we don't want to do this. Let's make a different choice for our term that we're going to save. Instead of saving cosine, we're going to save a sine. So we're saving one sine x for du. So our integral becomes sine squared x, cosine to the fourth x. We're saving the sine x dx for our du. And when we look at this, we say, well, if I'm saving sine x for my du, that means my u must be cosine, because the derivative of cosine is negative sine. Well, if my u is going to be cosine of x, I need to get rid of these sine squareds. So we convert these to cosines. Using the Pythagorean identity. So since we know that sine squared x plus cos squared x is equal to 1, we want to get an expression that has just sine squared x, so we subtract the cos squared x to the other side, and this is what we want to replace sine squared x with. So now this integral up here is going to be rewritten yet again. So sine squared x is going to be replaced with 1 minus cosine squared x. Then we have cosine to the fourth x. And then we have sine x dx. And what we can do now is we can take this whole thing and distribute it through the parentheses. This will give us 1 times cosine to the fourth x sine x dx, and then we have a minus, another integral. Now cosine squared times cosine to the fourth gives us cosine to the sixth x. We still have the sine x dx that we're distributing. Now we recall that u is cos of x, du is equal to negative sine x dx. And we say, well, we're missing the negative, so we'll adjust by putting a negative here and a negative there. And over here, I can take this negative inside, so it works. And now our integral is the negative integral of u to the 4th du plus the integral of u to the 6th du. So when we take the antiderivative, we have negative 1/5 u to the 5th plus 1/7 u to the 7th plus c. And then we recall that u is equal to cosine of x, so our final answer is negative 1/5 cosine to the 5th x plus 1/7 cosine to the 7th x plus c. And this is our answer to the integral. What was the strategy? The strategy, save a sine or cosine, convert others to match. In order to convert, we needed an even power to use the Pythagorean identity. So that was our first example. Let's look at our next example here. So again, the book tells us we're looking at a power of cosine that is odd and positive. You can take this and go back up to the rules and guidelines if you want to memorize them and use those. But instead, I want to reason with you as to why we make the choices that we end up making. Because sine is in the denominator, I would not save the sign for my dx, my du, I meant to say. Du can't be in the denominator when cosine is in the numerator, because the derivative of cosine would be negative sine, and that sign would need to be in the numerator. So with that said, since the sine of x can't be our du, if I choose cosine to be my du, how many cosines are left? So we're going to save a cosine instead. Save one cosine for du. Convert others to sine. So I'm going to pull the sine out of the denominator as sine x to the negative half power times cosine squared x times cosine x dx. We're saving this for our du. Since it's a definite integral, we're going to solve it. We're not going to use the plus c in our integration. So we know that cosine squared is going to be 1 minus sine squared. So when we distribute the sine through that parenthesis, we have sine to the negative half cosine x dx. Now we have a minus here, we see. And sine to the negative half times sine squared, that's going to subtract a half. It's going to be sine to the 3/2 power times cosine x dx. And now we see we're going to say let u equal sine of x, du equals cos x dx. There's no adjustment needed here because the derivative is not the negative of cosine, so everything matches up. With that said, we need to find the new bounds of integration. When I plug in pi over 6 into sine, we get 1/2. When we plug in pi over 3 into sine, we get root 3 over 2. And we changed our bounds to u. We're changing our integral to u. This is going to be u to the negative 1/2 du minus, bounds are 1/2 root 3 over 2, and this will be u to the 3/2 du. And now the antiderivative of u to the negative 1/2, you add 1 to the exponent, you get a positive 1/2. When you divide by 1/2, you get 2. So it's 2u to the 1/2 root 3 over 2 to 1/2 minus, when we add 1 to 3/2, we get 5/2. When we divide by 5/2, it's 2/5 u to the 5/2 root 3 over 2 to 1/2. And now we have 2 times root 3 over 2 to the 1/2 power minus 2 times 1/2 to the 1/2 power minus 2/5 root 3 over 2 to the 5/2 power minus 2/5 1/2 to the 5/2 power and I'll let you do the work here to simplify it, but the approximate decimal answer, if you want to check your work, is 0.239. Okay, so this is example 3, and example 3 we have cosine to the 4th power. Now this is one of the rules I said that I would use from the guidelines, where if cosine is an even power by itself, or sine is an even power by itself, we're going to use the power reducing formula. Or if you have both sine and cosine that are both even powers, we will use the power reducing formula. So the power reducing formula for cosine says that cosine squared of x is equal to 1 plus its cosine of 2x all over 2 there we go. And that means I need to express cosine to the 4th using powers of cosine to the 2nd. So we rewrite the integral of cosine squared of x in parentheses squared. And we say now I can replace cosine squared with its power reducing formula. So we have parentheses 1 plus cosine of 2x all over 2 squared. Forgot my dx's here. And now we want to FOIL 1 plus cosine of 2x. The denominator 2 squared is 1/4. We're just going to pull that out front. So 1 plus cosine of 2x squared is 1 plus 2 cosine of 2x plus cosine squared of 2x dx. And we say, okay, all of this is good, except now I have another cosine squared. I need to use power reducing again. So we'll write this integral again. We have our 1/4, 1 plus 2 times cosine of 2x plus, now cosine squared of 2x will give us 1 plus cosine of 4x all over 2 dx. So something to note here is when cosine had 1x, we doubled the angle to 2x. Now that cosine has 2x, we double the angle to 4x. So now we have a lot going on here. I'm going to separate these into their own integral each. So I have 1/4, the integral of 1 dx, plus 1/4, the integral of 2 cosine of 2x dx plus 1/4. The integral, this here is really a 1/2. So 1/2 dx plus 1/4. The integral, and this will be cosine of 4x over 2 dx. Zoom out a little bit so everything fits. Okay, so this first one's easy. The antiderivative of 1 is x, so we have x over 4. Here, this next one, we need to use u substitution. So let u equal 2x, then du equals 2 dx. We have our 2 dx. So this is plus 1/4 the integral of cosine u du. Here I have 1/4 times 1/2, that's 1/8, and we're going to get an x over 8 then from that. And this last one, we're going to have to say let u equal 4x, then du equals 4 dx. I need to multiply the dx by 4 and the out front by 1/4. So we have plus 1/4 times 1/4 is 1/16 times the 1/2 is 1/32. And I'm going to use a subscript of 2 because we have two different u's defined in here. So the antiderivative of cosine of u is sine u, but we understand that this u was a 2x, so it's sine of 2x. We can combine the x over 4 with x over 8. So this becomes 3x over 8 plus 1/4 sine of 2x. The antiderivative of cosine of u is sine of u, so it's plus 1 over 32 sine. Since this is u2, it's 4x. And then plus c is our constant of integration. And this is our final answer for this problem. And again, with these, you can check your answer in the textbook. These are the textbook examples. Or you can always use a tool like Wolfram Alpha to check your answers to see if you're doing them right. And just a word of advice, when you use Wolfram Alpha, you want to scroll down and look for alternate answers to find something that matches your format, because the computer likes to rewrite things in a condensed form. All right, so that's everything that we're covering on sine and cosine with our examples. Next, we have our secant and tangent examples. So these next examples are going to focus with powers of secant, powers of tangent. Again, the textbook has guidelines. If you want to memorize them and use them, that's fine. I'm going to go through the problems trying to make sense of why we're making the choices that we make, not just following a set of rules that are memorized. And in our first example, we have tangent cubed over the square root of secant x. There we go. So if we look at this example, we say, well, my secant's in the denominator. I probably wouldn't want to choose just secant to be my du. And there's a tricky example we can use here. We can say, well, if I use secant to be my u, then my du would be secant tan. And we say, well, I don't have secant tans in the top. So there comes this rearrangement. We're going to use some algebra to justify it. So when we look at this, the first thing we're going to do is just rewrite secant using negative exponents. And we we say, well, if I let secant be my u, then du is secant x tan x. If u is equal to tangent x, then du is secant squared x. And we look at these two and we say, well, how can we rearrange this to make this work? And this is the trick. Now that we've written secant squared x up here, if I factor out a secant tan, well, you say I only have a negative half secant. I don't have a whole secant. But if you factor out, you actually divide by that number or by that function. Just a side example. If I factored out a 4x squared from this, I'm sorry, just a 4x from this, we see that the second term here is easy to see that that would become just an x. The first one we say, well, that would become, the x's would cancel, but I don't have a 4 to factor out. So you have to ask yourself, what do I need to have to multiply back through here so I get a 4x? You say, well, what if I put a 1/4 there? 1/4 times 4x would give me just x. So when we factor out, we're actually dividing. So I actually divided this by 4x, my factor. And the x's canceled, and I was left with the 1/4. So let's go back and do that with our secant. Anytime we factor something out, we're actually dividing by that. So that means we're actually dividing by secant x tan x. The tangent's easy to see. That's going to be tangent squared. But the secant x, we're going to subtract 1. We're going to get secant to the 3/2. So it's just an algebra factoring rule. When we factor something out, the GCF that we factor out becomes the divisor. And when we divide it, we can adjust the powers accordingly. And now we have a secant x tan x. Well, if secant x tan x is what we're saving, that means we're going to be setting our u equal to secant. So now let's rewrite our integral. So the reason we saved all of this, the secant x tan x, is for our du. That means that secant is going to be u. And that means we have to convert the tangent x's by the Pythagorean identity. And we see that tangent squared x is equal to secant squared x minus 1. And now when we distribute this through, secant to the negative 3/2 times secant squared, we're going to add the exponents, we're left with secant to the half power. And then it gets the du paired up with it, because that gets distributed through the parentheses as well. And then we have a minus here. So our next integral is secant x to the negative 3/2, because secant x to the negative 3/2 times 1 remains unchanged. We pair it up with our secant x tan x. And now we can complete our u substitution. So we have u to the 1/2 du minus u to the negative 3/2 du. Negative 3/2 plus 1 is negative 1/2. When you divide by negative 1/2, that's a negative 2. So the negative of a negative 2 is positive 2 u to the negative 1/2 plus c. And we recall that u is secant x, so we have 2/3 secant x to the 2/3 or 3/2 power plus 2 secant x to the negative 1/2 power plus c. So here we have example 5, and we see that we have a mixture of powers. We have secant to the 4th of 3x, tangent to the 3rd of 3x. And again, we want to decide, what do we choose for u, what do we choose for du? So we just go through the motions. We say, what if? If u is equal to secant x, then du would be secant x tangent x. And we say, well, if this is the case, will I have even powers to convert, even powers of tangent to convert to secant? So we look at this, we say, all right, take out a secant x tangent x. That would leave me with secant to the 3rd of 3x, tangent squared 3x, and then we have our saved secant 3x tangent 3x. So, well, that works. I can have an even power of tangents. So I can convert it to secants using the Pythagorean identity. Now, just for comparison, let's look at if we chose a different u. What if u were equal to tangent x? I should actually say tangent of 3x. Then du would be secant squared 3x. Chain rule gives us 3 dx. And we say, okay, if I let the tangents be u, I need to save a secant squared. When I save a secant squared, are the secants that remain in even power so I can convert them? And the answer is yes. We would have secant squared 3x times tangent to the 3rd 3x, and then my saved secant squared 3x dx. And we say, yes, that would work also. So in this example, we can choose u as secant of 3x, we can choose u as tangent of 3x. Both cases will work. Great. Now it's just a matter of preference. So if we look at the textbook example lets u be tangent of 3x. So, as I've always done, I'll let you look at the textbook example and we'll do the other example. You can follow the textbook example. Let's work it out another way, just to show that we have choices to be made and different students will get different answers depending on their initial choices. So let's clear this. All right. So let's come back up here and fix what I had. It should have been secant of 3x. Okay, so if u is secant of 3x, Then du is secant 3x times tangent of 3x times the chain rule. The derivative of the inside is 3 dx. So that's what we need to save for our u substitution. And we said that when we use those components, we will have an even power of tangent left, so we can convert using Pythagorean identities. So secant cubed 3x, tangent squared 3x. That's what's left after we factor out a secant x tangent x. So secant 3x, tangent 3x dx. That's what we're saving for du. And now we go through the actual motions and say, okay, if u is equal to secant of 3x, then du is secant 3x tangent 3x times 3 dx. So I need to multiply this by 3, and I need to balance it by putting a 1/3 out here. And then we need to convert tangent squareds to secant squared 3x minus 1 by Pythagorean identity. Now I'm going to distribute the secant cubed through the Pythagorean identity. So secant cubed times secant squared gives me secant to the 5th 3x. Secant cubed times minus 1 is minus secant cubed 3x. And then all of this has my 3 secant 3x tangent 3x dx. And now we can write it in terms of u. And when we integrate, we have 1/6 u to the 6th minus 1/4 u to the 4th plus c. And our final answer, I'm going to distribute the 1/3. That gives me 1/18. I'm going to replace u with secant x, secant to the 6th 3x. Distribute 1/3 to 1/4. We have minus 1/12. Replace u with secant to the 4th 3x. And a constant times an unknown constant is still an unknown constant. So this is our example using the different substitution, the substitution where we let u be secant of 3x. Your textbook has the answer written out using tangent of 3x. So you can compare them both. You'll see there's a lot of similarities in them, except for the final function here is secant instead of tangent. But as far as the coefficients and the powers, you'll see a lot of similarity. Okay, so in example 6 here, we're looking at a definite integral of tangent to the 4th. And here, the trick that we're going to use is we're going to split tangent to the 4th into tangent squared times tangent squared. And then from there, we can use the Pythagorean identity. So now that we see that we have this, we say, well, let's convert one of these by Pythagorean identity. And when we distribute, we see that we get an integral that looks like this. And now, when we look at it, we say, well, if we let u be tangent here, then du is secant squared x dx. We say, well, that's an exact match. That's going to work out nicely. So the first integral is easy to do, but what do we do for the second integral? And the trick here is anytime you have tangent squared, you convert it using the Pythagorean identity. Because don't we know the antiderivative of secant squared? So we know this antiderivative. The antiderivative of secant squared is tangent. The antiderivative of 1 will be x. And we say, well, this side's easy. Here we use u substitution. So let's move on. Since we're changing this to u, we can say, well, since u is equal to tangent x, the new lower bound would be tangent of 0, which is 0. The new upper bound would be tangent of pi over 4, which is 1. The second integral keeps the bounds 0 to pi over 4 because we're not using a substitution. And I can just go ahead and integrate this. Tangent x minus x, pi over 4 to 0. And here we have 1/3 u to the third power 1 to 0 minus, if we plug in pi over 4, we get 1 minus pi over 4 minus 0 minus 0. So our final answer is 1/3 minus 0, and then we have minus 1 plus pi over 4. And we can combine these, and we get pi over 4 minus 2/3 as our final answer. So that one wasn't bad. The trick here is tangent squared. We want secant squared minus 1 because we know the antiderivative of secant squared. We know the antiderivative of 1. If we have tangent to the fourth, we want to rewrite that as tangent squared times tangent squared. Next question is, if we had tangent to the sixth, how would you rewrite that? And you should answer tangent to the fourth times tangent squared, so that you can always convert that tangent squared using a Pythagorean identity. So we just want to finish up with a couple of other topics. I'm not going to work these out. They're the simpler cases. Example 7 says converting to sines and cosines. If you can't recognize any of the benefits of secant squared and tangent, then you can convert secant squared and tangent using sine and cosine. And again, when I say the benefits, that means that you have a secant squared available to use as du, or you have a secant tangent to use as du if secant is your u. If you don't see any of those patterns, the worst case scenario is, okay, convert everything to its sine cosine definitions, cancel terms out, and then see if you can use sine and cosine as your u and du. So here's an example worked out, and that's something you can follow on your own and practice. And then there are integrals involving sine and cosine with different angles. That means what's in the parenthesis for each of them, the argument, don't match, and if they don't match, we have to use these formula here, these product to sum formula, or product to difference formulas, to give us something that we can integrate. So here we have sine of 5x, cosine of 4x. We see the angles don't match. So we use the product to sum formula, we convert it all, and we're able to integrate using u substitution. So these examples I leave for you to read on your own from the book, and then you should be able to complete the rest of the homeworks online now that we have the notes and you have the examples to follow. All right, and that's it.